Have you ever wondered how a self-driving car can detect a pedestrian hundreds of meters away, measure the exact shape of a moving vehicle, and build a complete three-dimensional map of the road without relying on daylight? The answer is hidden inside a device that never gets tired, never blinks, and never actually sees the world the way humans do. Instead of eyes, it uses pulses of laser light. Every second, millions of invisible laser pulses leave the sensor, race across the environment at the speed of light, strike countless objects, and return carrying tiny pieces of information. From those returning photons, the system reconstructs the entire world with astonishing precision. This is the engineering behind LiDAR, one of the most important technologies powering modern autonomous vehicles. LiDAR stands for light detection and ranging. Although the name sounds complex, the principle is surprisingly elegant. A laser pulse is emitted into the environment. The system waits for that pulse to return after reflecting from a surface. Because the speed of light is known with extraordinary accuracy, measuring the travel time allows the distance to every object to be calculated. One measurement means very little, but repeating that process millions of times every second creates a dense three-dimensional representation of everything surrounding the vehicle. Roads, buildings, traffic signs, bicycles, pedestrians, and other cars all become measurable geometry rather than simple images. The journey begins inside a tiny semiconductor laser. Electrical current flows through carefully engineered materials where electrons release photons as they transition between energy states. Those photons bounce back and forth inside an optical cavity, stimulating the emission of even more photons until a highly coherent beam of laser light is produced. Unlike an ordinary flashlight that spreads light in every direction, this beam remains extremely narrow and precisely controlled. Even microscopic instability could introduce measurement errors, so temperature regulation, optical alignment, and electrical timing are maintained with remarkable precision throughout operation. Producing a laser beam is only the beginning. A single stationary beam would reveal almost nothing about the surrounding world. The system must rapidly scan across the environment. Early automotive LiDAR units accomplish this by spinning the entire optical assembly, creating the familiar rotating sensors once mounted on prototype autonomous vehicles. Modern designs increasingly replace large mechanical motion with microscopic MEMS mirrors or optical phased arrays capable of steering laser beams electronically. These technologies dramatically increase reliability while allowing hundreds of thousands of measurement directions to be covered in fractions of a second. Once emitted, every laser pulse begins an extraordinary journey. Traveling at nearly 300 million meters per second, the beam may strike asphalt, painted lane markings, reflective traffic signs, glass windows, metallic vehicles, trees, or pedestrians crossing the street. Every material reflects light differently. Smooth, reflective surfaces return strong signals, while darker materials scatter more energy away from the sensor. Yet even when only a tiny fraction of the original light returns, the LiDAR system is designed to detect it. The returning photons enter a carefully designed optical receiver where precision lenses collect and concentrate the faint reflections onto an extremely sensitive detector. Many automotive LiDAR systems rely on Avalanche photodiodes or single photon avalanche diodes capable of detecting incredibly weak bursts of light. Inside these devices, even a single arriving photon can trigger an electrical avalanche that amplifies the signal into something measurable by electronic circuits. This extraordinary sensitivity allows the system to recognize reflections that would otherwise disappear into background noise. At the heart of every distance measurement lies an astonishing exercise in timing. The processor records the exact instant each laser pulse leaves the transmitter. It then measures the precise moment the reflected photons arrive back at the receiver. The difference between those two events represents the total travel time of the light, since the pulse travels to the object and back again. Dividing the total distance by 2 reveals the object's actual position. These calculations occur with timing precision measured in billionths of a second, enabling centimeter-level accuracy across large distances. While millions of measurements are processed continuously, one measurement creates only a single point in space. Millions of measurements create something far more powerful, a point cloud. Every reflected pulse becomes a three-dimensional coordinate representing a real location in the environment. Together, these coordinates form an incredibly detailed digital model of the world. Vehicles emerge as recognizable shapes. Buildings become precise structures. Trees reveal their branches. Road barriers, traffic signs, and pedestrians all appear as dense clusters of measurable points. Unlike ordinary photographs, this representation contains true spatial information rather than only color and brightness. The point cloud is then handed to advanced perception software powered by artificial intelligence. Sophisticated algorithms examine the geometry, density, movement, and relationships between millions of points to determine what each object actually is. A parked vehicle can be distinguished from a moving truck. A cyclist can be separated from a pedestrian. Temporary construction barriers can be identified alongside permanent roadside structures. As new scans arrive many times every second, the system continuously tracks movement, predicts future trajectories, and estimates how every object around the vehicle is likely to behave during the next few moments. All of this information ultimately reaches the vehicle's decision-making system. Steering, braking, acceleration, and obstacle avoidance all depend on the accuracy of the measurements generated only fractions of a second earlier. If another vehicle suddenly changes lanes, if a pedestrian steps into the road, or if unexpected debris appears ahead, the LiDAR data contributes to the calculations that determine the safest possible response. The entire sensing, processing, prediction, and control pipeline repeats continuously while the vehicle is moving, allowing it to react far faster than any human could manually perform millions of optical measurements. The next time you see a self-driving vehicle navigating busy streets, remember that it is not simply looking at the world. Hidden inside its sensor is an invisible orchestra of lasers, optics, semiconductor detectors, high-speed processors, and artificial intelligence working together with extraordinary precision. Every returning photon carries a tiny fragment of reality. Millions of those fragments are assembled into a living three-dimensional map that updates almost instantly. Long before a human driver could consciously recognize every detail ahead, LiDAR has already measured it, calculated it, classified it, and transformed invisible pulses of light into the machine's understanding of the world.